This video is based on some talks I gave in 2023 and 2024 to 3 or 4 different groups about mean wind and turbulence profiles over the open seas and oceans. You can see from the images there that the surface of particularly the open ocean is actually quite varying depending on storm conditions, wind conditions generally. You can say it's generally smoother roughness, less rough than the surface of land. What that means is that the wind speeds tend to be higher over the open oceans and open seas. The one on the right is actually taken from an aircraft flying into a hurricane, and it showed that actually the surface was quite flat. There's a lot of white water there, but it was actually quite flat. But there is generally a dependency of the surface roughness, which does affect the wind profiles and the turbulence, as a function of the wind speed itself. So that's an extra complexity that you don't normally consider when you're looking at wind over the land. Well, these images show the kind of structures we're interested in from a structural design point of view that you will find in the oceans. So we have offshore oil and gas platforms on the left, and the equivalent renewable energy structures, offshore wind turbine towers on the right. So we're particularly interested in the strong end of the wind range for these structures, interested in their design. So we're talking about typically 25 meters per second and above, based on winds at a height of 10 meters. I'll be claiming later in the talk that in that strong wind range of interest to design of structures structurally offshore, I'll be claiming that the surface roughness remains pretty constant above a mean wind speed at 10 meters of about 25 meters per second. So that's where the roughness saturation in the title comes in. Before discussing that, though, in the talk I'll talk quite a bit about the Charnock relationship, realizing that tends to get applied over a wide wind speed range. My contention will be, though, it shouldn't really be applied more than about 20 meters per second. Now, there are existing design standards for both these types of structures. You see the covers at the bottom. These are international standards. There's ISO standard for mid-ocean design for oil and gas structures. And we have International Electrotechnical Commission, IEC, standard for wind turbine or wind farm structures. These are not very, in terms of their wind profiles and turbulence profiles, they're not very similar to each other. In fact, for the wind turbine, there is only one standard that supposedly covers on-land wind farms as well as offshore wind farms. Now, most people here have heard the name Henry Charnock, I would imagine. He was a pioneer of wind over water and wind stress on a water surface. He had a very famous paper from 1955. That's the whole paper in the middle of the slide there. It's actually a summary of a talk I think he gave to the Royal Meteorological Society in London. And his idea was that the wind profile over the ocean or any water surface should follow the logarithmic law, which is a general boundary layer equation, which is on the top right, reproduced on the top right. Now, he suggested that the roughness length in that logarithmic law should be, by dimensional analysis, proportional to the shear velocity squared divided by the gravitational constant, so u star squared over g, and the arbitrary constant in that relationship is known as Charnock's constant A, which is non-dimensional. Now, it's a little bit confusing. Halfway down his paper there, he has another constant which is not the same as little a. I've called it uppercase A. That's the relationship between those two constants. But unfortunately, as I'll show in a minute, the Charnock's so-called constant is not really very constant. People come up with all different values. based on measurements. But I think it's a very useful benchmark for wind profiles generally over the ocean. Now, a more popular measure of surface roughness is, rather than the roughness length, which has got dimensions of length, meters or millimeters, for example, a more popular measure is the surface drag coefficient, which is non-dimensional. And that's defined as the shear velocity squared divided by the mean wind speed at some reference height, which is typically 10 meters above the surface. So the second line there, you see the definition of CD10. Now, if you apply the log law at a height, Z, of 10 meters, you get a relationship between roughness length and surface drag coefficient. The next line there, the third line. Now, if we apply the Charnock relationship for Z0, we get that second equation there, which is a bit more complex, but that is an implicit relationship between surface drag coefficient and mean wind speed. And the fourth line there, we've taken that implicit relationship between CD10 and U10. We've taken the U10 over to the left-hand side. So now it becomes an explicit relation between mean wind speed at 10 meters and the surface drag coefficient. That's denoted by equation 1. It's explicit, but it's non-linear. We can plot that expression for a range of values of the Charnock constant, and that's done on the graph at the bottom. So you see various values there of Charnock constant between 0.005 and 0.025. I think that covers the probable range of values that people have come up with over the years. It's interesting that those plots, they all sort of converge together at the left-hand end, at the low wind speed end. But you'll notice there's a fairly linear relationship between about 5, 6 or 7 meters per second to 25 meters per second. So that Charnock expression, equation 1, even though it's non-linear, it reverts to something that's pretty close to linear over quite a long range of wind speeds. Well, after fiddling around myself earlier this year trying to justify the linear variation that comes out of the Charnock nonlinear expression, I found somebody had done a pretty good job already, and Guan and Xi in the Journal of Physical Oceanography 2004 had an interesting paper where they, instead of plotting the surface drag coefficient against the mean wind speed directly, they plotted CD10 against a non-dimensional parameter they call y, which is shown on the left, the equation on the top left there. That's non-dimensional since the 10 is actually 10 meters. So the bottom line of that on the right-hand side is the denominator on the right-hand side is actually a velocity. So then that nonlinear expression I showed previously on the previous slide reverts to the one shown there in terms of y. So then they fitted, using least squares fitting, CD10 against y, and you see the graph there on the top right. They ended up with this sort of universal linear fit. CD is 0.78 plus 4.7y times 10 to the minus 3. So I thought that was quite interesting. And just to check to see how that works out, you can differentiate their expression for y with respect to, or you can differentiate CD with respect to y, and that's the bottom right equation there. And you plot that one, and then you see the orange curve at the bottom, so that's the slope of the top curve. And there is a range of y between roughly about 0.1 to 0.4, which is fairly constant. The slope is fairly constant, so that represents a straight line relationship of CD against y. It's valid not for the whole range. It's less than 0.1 or y 0.1. It doesn't really work. And 0.4 is actually about the range of measurements that the Charnock relationship applies to. So we can say that the linearization is valid from roughly about 6 meters per second to about 25 meters per second, which corresponds to y of 0.1 to 0.4. So now plotting the Guan-Yong's linear fits to the Charnock expressions and superimposing those on the plot, you see the dashed lines there on the graph. You can see the range in which the linear fit is applicable, probably from about 5 meters per second upwards. But then below that limit, they all converge down to a common intercept of 0.78 by 10 to the minus 3 on the CD axis. The slopes of the lines are proportional to the square root of the Charnock so-called constant. So this slide just shows the linear fits to the Charnock expression according to Guan-Yung, and the mathematical expression with respect to U10 is shown on the right hand side there. So the intercept, as I mentioned earlier, is 0.78 times 10 to the minus 3. That's independent of the Charnock constant. The slopes is dependent on the Charnock constant, is equal to 0.475 by 10 to the minus 3 times the square root of A. So when you vary a Charnock constant, you get a different slope there, and that shows on the plots there. Now, from the middle of the 20th century onwards, there have been a lot of measurements of surface drag coefficient for overwater winds, below about 20 or 25 meters per second, I should say, so we haven't really got into the structural design range yet. But those measurements and papers that summarize them pretty much use linear relationship between CD and the mean wind speed at 10 meters. And you see a table of authors there, and their various values of intercept and slope. Now, you won't see too many there of, well, there's a range of intercepts. So the 0.78 is not a universal value based on measurements. You've got a big range of values. But I should say those measurements there that are shown, I think only a couple of them relate to wind over the ocean. Some of them are wind over small channels and bays. Some are even made from laboratory measurements. But those two I've ringed there at the bottom, they are over the open ocean. So it looks like for open ocean winds that the intercept is more like 0.5 to 0.6 by 10 to the minus 3 rather than 0.78. Now looking at the ISO standard, which is intended to cover mid-ocean design for oil and gas structures, that is the linear expression in that particular standard for surface drag coefficient against mean wind speed. You'll see the intercept there is actually 0.525 by 10 to the minus 3. Now that expression is based on measurements of recorded data from Frøya, which is an island off Norway. I'll show it on the next slide. So we'll be talking quite a bit about those particular measurements. It's probably still the best data around, even though they're 30 or 40 years old already. I haven't seen anything any better than that covers a range of heights and wind speeds. So you can see from the two maps this island of Frøya, which is off the west coast of Norway. The west end of that island is exposed to gales from the Atlantic, from the west and southwest, and the people that did the measurements, which I believe was funded by the State Oil Company of Norway, over a period of 2 or 3 years, they erected 3 towers, I think up to 100 meters, and collected a lot of data, profiles of wind speed and turbulence over that period. Now, on the right-hand side, you see the two journal publications where this data is discussed. The first one on the top is describes the instrumentation and the database. the second one in the Marine Structures Journal describes summary of the results. Now, there was a lengthy report that gives a lot more detail, but if you just want to get the summary, you'll find it in that paper on the right at the bottom there. It was a good set of data, but unfortunately the measurement stopped at about 26 meters per second at 10 meter. It's a pity they couldn't go a bit higher than that in retrospect, but I guess they didn't stay there long enough to get any higher values. Well, this graph shows a plot of surface drag coefficient against reference wind speed, which is the 10 meter height wind speed, and you can see the points there. They were pretty much on a linear relationship, at least up to about 22 or 23 meters per second. But it's interesting that paper reporting on the Fourier data from Anderson and Lovsev mentioned that, or noted that the data indicated saturation, implying that the surface drag coefficient sort of tended to reach a maximum value at around 23, 25 meters per second. As you can see, ringed in red there. So we're going to follow up on that idea a bit later in this talk here. Well, another important set of measurements over the ocean in very strong winds, based on hurricanes actually, were made by the Hurricane Center in the United States, flying aircraft into these storms, dropping probes into them, and tracking their position and speed using GPS satellites. You can see the probe, the diagram of the probe over on the right there. These are quite light cardboard probes, disposable probes, and they're interesting. They had a large number of flights and a large number of drops of these probes. If you do enough averaging, you can produce velocity profiles through the storm at different radial positions in the storm. And in the middle of the graph there, you'll see a plot of surface drag coefficient against 10 meter wind speed, similar to earlier plots on the earlier slides there. And these are all based on these drop sondes or drop wind sondes that I just mentioned there. So, and the references down the bottom there, Powell et al. 2003. So interesting graph there, but it looks like the surface drag coefficient sort of reaches a maximum and maybe even drops off above about 40 meters per second. There's a fair amount of scatter in this measurement technique, as you might expect, and the response of these probes is a bit uncertain, but if you do enough averaging, you get a reasonable idea of the surface drag coefficient. But it looks like there is an upper limit of about 0.0025 of the surface drag coefficient obtained from those measurements in hurricanes. So it's interesting to know what is actually going on in this saturation region. As it happened, from the aircraft that were flying into these hurricanes, they fly at fairly low level above the surface, that we have some images of the sea surface during these very high wind speeds. That particular image was about 34 meters per second apparently. You can see, a little murky there, but you can see the surface consists of patches of foam 20 to 50 meter wide, and as it says, they're caused by the wave faces breaking and being sheared off by the wind. So that's one explanation of the relatively low surface roughness that you do get at those high wind speeds. So now moving on to what I'm proposing for the model for surface drag coefficient as a function of wind speed. Essentially, it's taking the Fourier data from Norway that I showed earlier, fitting a straight line up to 25 meters per second, which does give you a surface drag coefficient of 0.0025, and then making it constant beyond that So that's because of this saturation or capping that we think is occurring at higher wind speeds. So that's the solid blue line there on the plot. Now that function up to 25 meters a second is actually taken directly from the ISO standard that I showed earlier for metocean for offshore structures in the oil and gas industry. The difference with that ISO model though is that it's extrapolated beyond 25 meters per second. There's no upper limit on the surface drag coefficient. But I'm suggesting there should be an upper limit based on the value at about 25 meters per second. So down the bottom there you'll see the proposed equation for surface drag coefficient as a function of wind speed at 10 meters. And of course if you use those values with the logarithmic law, you'll get that defines mean velocity profiles over the ocean at a range of wind speeds. Now moving on to longitudinal turbulence intensity, what we're showing here are some measurements of turbulence intensity at a height range of 46 meters above the surface, plus or minus 13 meters. So some of these measurements, the black triangles, are from oil platforms in the Gulf of Mexico and Atlantic in that height range. The circles are from average data from the Fourier measurements, which of course finish at 26 meters per second. And then the dashed line there is the ISO expression from ISO 19901-1. Now you wouldn't say that was a great fit to the data. At the bottom end, at the low end, below 25 meters per second, it underestimates the Fourier data. At the high end, it probably overestimates the recorded values. So we'll see if we can do a bit better. So we try to improve the fit by changing one of the constants in the ISO expression. You might recall from the previous slide there, the coefficient of the wind speed in that term was 0.043. We've increased that to 0.05 in the top line there. Now above 25 meters per second, we've made the longitudinal turbulence intensity constant, as we did previously with the surface drag coefficient. So that gives us the height dependent formula of 0.135 Z on 10 to the negative 0.22. So we've ended up with the blue line there, which is definitely a better fit to the recorded data at both ends, the low and high wind speed ends. So this is a similar plot to the previous couple of slides there, except at a different height. This time it's a height of 10 meters. So there were some automatic weather stations in offshore islands and a reef. One island and two reefs as a tropical cyclone approached the coast of Queensland in 2011, quite a strong cyclone. And we had a series of gust factor measurements, so 3-second gust over a 10-minute mean, from which you can extract turbulence intensity. You just need a peak factor, which doesn't vary very much. So those black dots there are these readings from different times and 3 different locations at a height of 10 meters. And we're showing the ISO line there again as a dashed line, and then the proposed function for that height of as a blue line there. And so I think you can say that the proposed one is not a bad fit, especially gives you a constant value above 25 meters per second, which seems to fit the data a bit better. Well, this is another graph of turbulence intensity measurements over the ocean. This time it's for wind speeds that are greater than 25 meters a second, so they might be around 30 to 35 meters per second generally. But we're assuming that we've got a sort of a constant, at a given height, we've got a constant turbulence intensity for wind speeds greater than 25 meters per second. So sort of checking that idea, we plotted a number of measurements on the same graph there, compared it with what we are proposing for mean wind speeds greater than 25 meters per second, that dashed line there. So as well as the the Freya measurements don't appear on here because their measurements were less than 26 meters per second at least. But we do have some US hurricane data from those platforms. We also have Cyclone Yasi, which hit Queensland, Australia in 2011. There were measurements at 10 meters on several reefs and islands as the cyclone approached. And we've got measurements from Japan and also some more recent ones from the North Sea, the Fin 1 and Fin 3 platforms, which are off the coast of Germany, I think. So those are at a height of about 80 meters. So we've got a bunch of different readings there, and they're all individual readings, so there's got to be a bit of scatter with them. But generally that dash line fits the general trend, I think, fairly well. So this adjusted ISO equation seems to fit pretty well for longitudinal turbulence intensity. I should admit I stole the sort of Fin 1 and Fin 3 measurements from one of Gus's papers. So thank you, Gus, for that. So coming to the conclusions, the first one, the Charnock equation, which is commonly used for surface roughness or roughness length, and you can adapt it for surface drag coefficient. It's closely equivalent to a straight line relationship over quite a wide range of wind speeds, above about 5 or 6 meters per second. But the intercept is not matched by the measurements. It gives, according at least to the Guan-G model, you should get an invariant intercept irrespective of the Charnock constant, 0.78 by 10 to minus 3. That doesn't seem to be the case in the measurements. Second one, importantly, this is an important conclusion, that the measurements are indicating a capping or saturation of the surface roughness, surface drag coefficient, and also the roughness length. That's apparent in the Freya data and in Atlantic hurricanes. It also appears when you plot the turbulence intensity as well, which is directly related to the roughness, of course. So that appears to give a maximum surface drag coefficient of about 2.5 times 10 to the minus 3. That's equivalent to a maximum roughness length of 3.35 millimeters. Now, if we take the ISO model from the ISO standard for mid-ocean, then we adjust it a little bit. In particular, we cap it at 25 meters per second and also adjust the turbulence intensity a little bit. We seem to get better fits to the recorded data for both surface drag coefficient and turbulence intensities. And that new proposed model will give you constant roughness and constant turbulence intensity. Well, turbulence intensity is only a function of height and not mean wind speed above 25 meters per second. Now, for engineering design, that's usually the range you're interested in for structural design. So it's the high end of the wind speed. So having velocity dependent parameters, surface drag and turbulence intensity, is quite convenient. Now, when I present this previously, people are asking, well, what are the physical explanations for the capping and saturation? Well, I showed you the images from the aircraft flying into the hurricanes, so that gives you some idea of what's going on there. There have been 2 or 3 papers with different explanations for this capping and saturation in the last 20 odd years. So I think the jury is still out a little bit, and maybe there's more than one physical explanation for it. But the trend is there in the data, and it's fairly convenient for engineering design, so I think we can live with that.